Hi everybody, welcome to another video in differential equations, section 4.6, variation of parameters. So on previous section we deal with non-homogeneous equation. So that is the equation that has something not equal to 0 on the right hand side. Previous section we use the method what we call the guessing method. The problem with the guessing method is it has to be in some certain forms for us to guess. If it is in different form, we cannot guess. An example for that is if it is tangent, we cannot guess the form for the particular solution, and that is the problem. If you cannot guess, there must be another way to do it. Right. So what we're looking for is the solution will be in this form. Of course, y1 and y2 are the solution in the complementary solution. Complementary solution is y1 c1 y1 plus c2 y2, the combination, linear combination of y1 y2. So this is complementary solution. This comes from homogeneous equation. Come from the equation equal to 0. Same equation, but the right hand side is equal to 0. So make it equal to 0. So for that first, give us complementary solution. This is exactly the same as previous section. We always have to do that. Even we just guess the particular form, always have to guess. Always have to solve for the complementary solution first to see if there is anything that is not linearly independent. In that case, we have to multiply by something, so the particular solution will be linearly independent to the complementary solution, part of it. Right. So always have to do that first. That's the first step. Next, now the fundamental in variation of parameter is that we assume the solution will be in this form. This is the variation from the y1 and y2 in the complementary solution. We're going to solve for v1 and v2. Could be function. Right. Then because we take derivative, second derivative, put in a function and simplify. That would be a lot of work and a lot tedious work. Now, but what we let after that is since y1 and y2 are solution, this bracket equal to 0, this bracket equal to 0, and we're going to have this, which give us this one. And finally, so once again, very important that the solution will be in this form of variation parameters for particular solution. And how do we solve for v1, v2? Well, in order to solve for v1, v2, we have to solve for this system of equation. Now, system of equation, we can use different ways, substitution, elimination. But when things get complicated with all the different functions, it is better to use the Cramer's rule. So Cramer's rule is that first, by the way, the variables here in this system of equation is v1 prime and v2 prime. Those are the variables here. Now, if those are the variable y1, y2, y1 prime, y2 prime, those are coefficient. And if you put all of that into the coefficient, we have a 2 by 2 determinant. The reason I use W because that also is going to wrong skin y1, y2. Of course, we did say about linearly independent. The wrong skin should not be equal to 0. Right. So put all of that on the coefficient into W. Now the W1, in order to get W1, what we do is replace the last column into the first column. And W2 replace the last column into the coefficient here. Right? Replace that into y1 here. Yeah. Just put that column into y1, y1 prime. give us W1. If we put that in the second column, that gives us W2. And those are determinants. Evaluate the determinant. Let's divide them. And then we will have V1 prime is W1 over W. V2 prime is W2 over W. And one we have V1 prime, V2 prime, integrate them. And finally, since we know V1 and V2, put it back in this form, we have a particular solution. The nice thing about this is, even though that looks complicated, but it's actually it is complicated, but the reason it is complicated because of the calculus part. What we actually do is not that much. We set up the variation parameters and then the system of equation for V1 prime and V2 prime. The problem will be complicated if the integration is complicated. Which one we have V1 and V2, we're just going to have that. The nice thing about this is we don't have to solve for the undetermined coefficient. Whatever we have for a particular solution will be a particular solution, which certainly works. We don't have to worry about or the coefficient or guessing, so there's no guessing here. We just go straight to the solution. Right, so let's look at one example that has the workout solution. So this is our problem. Yeah, and if it is tangent of t, we cannot guess. We cannot guess for a particular solution, so there must be a different way. By the way, what I do here might be different than what we have in the book. So if you read the textbook, I think that is rather confusing. So the way I do it, first thing, if it is equal to something like that, always divide to get the first coefficient to be 1. So divide everything by the leading coefficient. What I want is just leading coefficient is 1. That will save us a lot of the calculation later. Right. Now, complementary solution. So we just have for homogeneous equation, just make them equal to 0. And this is a homogeneous equation. And we can get, for complementary solution, we go for the homogeneous equation. And because that, we set up the auxiliary equation. So for those values, and y1 is this, y2 is that. Right? Now, let me be a little more clear about this. Usually, I can write this as 0 plus or minus 1 times I. Now, because if it is in imaginary form like that, then the solution will be y1 is equal to e to the alpha t cosine of beta t, and y2 similar, but it is sine instead of cosine. E to the 0 power is 1. Yeah, so e to 0 power is 1, so we just have cosine and sine. Because of that, so we do need to know what is y1, what is y2. So we have y1 and y2, and then of course complementary solution is that. Now, to our particular solution, we have to guess. I mean, not guess, particular solution. If we cannot guess, we can use the solution. Assume we take this form: v1 prime y1 v2, I mean v1 y1 plus v2 y2. Now, how do we solve for v1 and v2? Well, we're going to put in the equation. When we set up the particular solution in that form, we can write the system of equation. By the way, every problem will be exactly like this. Find y1, y2, particular solution will be in that form, and we solve for the system equation. The system equation variable is v1 prime and v2 prime equal to f over a. Now, I did say that just try to get the first coefficient is 1. If this is 1, always do that. Try to get the leading coefficient to be 1 in our problem. So in that case, whatever that will go into the right hand side. So y1 plus v1, y1 v1 prime plus y2 v2 prime equal to 0, and y1 prime v1 prime plus y2 prime v2 prime is equal to whatever that function is. Every problem is like that. Every problem. So now when we do a field problem, then we get the idea. Now when for this we set up the coefficient y1, y2, y1 prime, y2 prime, Cosecant, determinant 2 by 2, cross multiply and subtract, we have 1. Find w1, w2, and then the grammar rule say, there's a typo here, the first variable is equal to w1 over w, second variable is equal to w2 over w, so we have those two. Finally, we have the derivative. To get back to the function, we integrate. Integral of sine t tangent t, and we write like that, and that is v1, and v2 integrate that, I have it. Of course, there's no need for the constant c here. And finally, put it back into the variation of parameters, the solution. Put everything in that, and then there will be something to simplify, I believe. Sine t, cosine t, sine t, cosine t cancel out, and we have that. So the fundamental here is get y1, y2, particular solution will be in this form, and solve for that system of equation using Cramer's rule. Right, let's look at the first example. See what we get. Right, so this is what we have. So as mentioned before, if it's the case, first thing, just divide by 4. I prefer to have the equation that with the 1 as the leading coefficient. Divide by 4, that's what I mean. So divide by 4 on both sides, we have 4y double prime. There's no more 4. Y double prime plus 9 y equal to 1/4 cosecant of 3x. Right, because it is cosecant, we cannot guess. If it is sine or cosine, yeah, we can guess, but it is cosecant. No. So the first step, right, this is not difficult. The difficult part is the calculus part. The steps are very clear, so I will write very slow on the step. So first, we need to solve for a complementary solution. So in that case, we write the homogeneous equation. So assume that equal to 0 and auxiliary equation. So homogeneous equation try to write small because this one will take a lot of space. And that is the homogeneous equation. We have the auxiliary equation. second derivative corresponding to r squared, and the function will be just 9 equal to 0. Now r squared plus 9 equal to 0. So we have r squared equal to 9, negative 9. So r equal to plus or minus square root of negative 9 will be plus or minus negative inside square root, that imaginary, plus or minus 3i. So similar to the last problem, the solution would be, of course, if you can't, we can write also 0 plus or minus 3i. So in that case, y1 is e to the alpha t. In this case, the variable is x term, so use x. By the way, on the test, if you happen to write the x instead of t or t instead of x, and my MATLAB count it wrong, send me an email with that question. I will go back and give you the grade for that one, because the variable is not really important. What important is if you do the math correctly. So cosine of beta x e to 0 power is 1. So this is just cosine of 3x. Y2 e to 0x sine of 3x. Yeah. So the real part goes to the exponential. The imaginary part goes to the trig function. E to 0 power is 1. So this is just sine of 3x. So the complementary solution is complementary solution C1 y1 plus C2 y2. So C1 cosine of 3x plus C2 sine of 3x. Alright, so we have y1 and y2. Now, we do need that for variation of parameters. So second part, of course, is for the particular solution. So particular solution in variation parameters will take this form of v1 y1 plus v2 y2. So just write. So once we find y1 mean v1 y1 y2 variation parameters and this system of equation, where we have the system equation y1 v1 prime plus y2 v2 prime equal to 0, and take derivative, because this looks like the wrong skin, v2 equal to f over 8. Now if this is coefficient is 1, we're just going to take the input function. So it's going to be just that. So this is called the input function or the non-homogeneous term. If this is 1, that's going to go into this equation. So it's important to write a note here. If leading coefficient is 1, I mean 1's here, then this is the input function. Will be equal to this. Don't have to do anything else. Would you just go directly here? So that's why I want to divide by the leading coefficient first to get this one. So in that case, whatever the function on the right hand side, move there. The book might do that differently, but I recommend that we do it this way. Yeah, just get that to 1 and then put that there. Now, this is a system of equation where we use the Cramer's rule. So Cramer's rule. First, I will write W, which is the determinant, 2 by 2 determinant, because this one has 2 equations, y1, y2, y1 prime, y2 prime. So this is just a Wronskian. And we know that this is not equal to 0, because if this is equal to 0, they are not linearly independent. And because these two are linearly independent, the Wronskian is not going to be equal to 0. Right, let's do that first. y1 cosine of 3x, y2 sine of 3x. Now take derivative. Cosine of 3x is negative 3 sine of 3x. Derivative of this is 3 cosine of 3x. Now, cross multiply and subtract. We have 3 cosine square of 3x minus a negative 3 minus this direction should minus another minus, so that's plus. Yeah, the same minus negative 3 sine square of 3x. So that gives us 3 cosine square plus 3 cosine square. You can factor out the 3. And sine square plus cosine square is 1. So that is the W. Now, W1, I will just replace this column, the last column, into the V1, Y1. So instead of Y1 prime, Y2 prime, I will put that in here. 0, 1/4. By the way, 3 times 1 is 3. Right. So I put the last column into Y1. Instead of Y1 prime, I put the last column in. And then still Y2 and Y2 prime. Right, 0, 1/4 cosecant of 3x sine 3x, 3 times cosine of 3x. I did say that you need to write very small because this might take a lot of space. Right, cross multiply, that's 0, and we have negative times this 2, 1/4 cosecant of 3x times sine of 3x. Now, cosecant is 1 over sine, right? So we have negative 1/4. Cosecant is 1 over sine. So conveniently they cancel out. We have negative 1/4. So that is W1. W2, we will replace this column, the last column, into Y2 and Y2 prime in the wrong skin. By the way, I said it in the book, they do it differently and rather confusing. This one is a lot more systematic. Right? Y1, Y that. Sorry, I didn't even pay attention. Put that into Y2 and Y2 prime, so Y1 and Y1 prime still there. One-fourth cosecant of 3x. Right, y1 prime cosine of 3x, negative 3 sine of 3x. And then 0, 1/4 cosecant of 3x. Cross multiply and subtract, we just have those two because this is 0. So we have 1/4 cosine 3x times cosecant of 3x. Cosecant is 1 over sine, so cosecant is 1 over sine, and move that to the bottom, right? Cosine over sine is cotangent, 1/4 cotangent of 3x. Now we have all the w's. Now once we have the w's, the Cramer's rule said v1 prime is w1 over w, still has the derivative, right? W1 negative 1/4, W3, well, that should be easy, so that's negative 1 over 12. Right? Now that's too easy. If the derivative is negative 1 over 12, to get back to V1, I just integrate. And that is negative 1 over 12 x. Don't need a constant here. Then V2 prime is equal to W2 over W. Right? W2 is that cotangent. Over 3, which is W. And that gives us 1 over 12. Cotangent of 3x. So if that is the derivative, to solve for cotangent, we need to integrate. Integrate of 1 over 12 cotangent of 3x. Right. Of course, if you remember cotangent, the integral of cotangent, that would be great. If not, we can use a substitution. Yeah. I remember, but I'm not sure, so I'm just going to write that as a quotient. Will be cosine of 3x over 12 sine of 3x, because that's what cotangent is, cosine over sine. Right. Now I try to write, utilize this space here for the substitution. If I let u equal to the bottom sine of 3x, then derivative is 3 cosine 3x, right? Swing the dx over. And if you solve for dx, will be du, sorry, kind of small, but if you solve for dx, divide 3 cosine 3x on the other side. Right. For that, I can substitute into dx. Cosine 3x still there. 12. Now sine of 3x, we only did let that equal to u, so times u. Dx is going to be du over 3 cosine of 3x. Cancel out. 12 and 3, that gives us 1 over 36. Come outside of the integral. Yeah, 3 times 12 is 36. Everything cancel out except 1 over u du. Integral of that is ln of absolute values of u, and 1 over 36 ln of u, which is sine of 3x. Right, so we have V2. And finally, particular solution. V1, Y1, V2, Y2. V1, what is V1? Negative 12, 1 over 12x. Y1, cosine of 3x. And then plus V2, 1 over 36 ln sine of 3x. And then y2 sine of 3x. Right, so we have the particular solution. And really hate this, but we run out of space. But if we want the general solution, we just say y equal to complementary solution plus particular solution. So the solution is, this is the complementary solution. C1 cosine 3x plus C2 sine of 3x. And that plus the particular solution will be this, minus 112 x cosine 3x 1 over 36 ln sine 3x, sine 3x. Yeah. So the complementary solution, particular solution, and then that. Right. Yeah. This is not important. The important here is we get the particular solution. As you see, we don't need to solve for the undetermined coefficient. So the coefficient come out perfectly. So yeah, I write a few more steps than I need to, but we have complementary solution. Get that. What we get is we need to know what is y1 and y2. Once we have y1 and y2, the solution, particular solution, would be in that form of this system equation. Using Cramer's rule, we have w, w1, w2. After that, v1 prime is w1 over w, v2 prime is w2 over w. We have the derivative, integrate to get back to the function. And finally, put things together, we have the equation. Thing together. Solution is complementary solution plus particular solution. That's what we have. So it's not that difficult. The differential equation part is the steps are clear. Solve that equation and then integrate. The difficult part is sometimes the integral is not very friendly to do. Right, let's look at another example. This one. Right, now, unlike the last problem, the right hand side, the input function is cosecant. If it's cosecant, we cannot really guess. We can certainly guess the solution here. Right, let's look at this. So the first step, of course, I still look at complementary solution. Again, try to write small. Complementary solution. So start with the homogeneous equation and then auxiliary equation. So make this equal to 0 to have the auxiliary equation. So homogeneous equation. Again, the leading coefficient is 1, which is good. Homogeneous equation is when that equal to 0, and then we can get the auxiliary equation. Which is r squared minus 4r plus 4 equal to 0. Sorry, kind of small. Right, r squared minus 4r plus 4 equal to 0. If we solve for that, the factor would be r minus 2 times r minus 2. So if r equal to 2, this is a double root. Or we can write r1, 2 equal to 2. Yeah, so two solutions are the same. Right, because of that, so y1 equal to e to the that power times t, and y2 has to be linearly independent to that. So we cannot say e to the 2t, even though both of them have 2. We have to multiply t to it to make it linearly independent. Right, so that's what we have. Now, I did say that this problem we can guess. So if we have to guess the solution, what do we guess? we have a polynomial here. So I write that in general, e to the 2t. So if I guess that, let's multiply it out. If I guess that, this solution is exactly as that, so it's not good, right? Because I have e to the 2t, e to the 2t, and t, e to the 2t, t e to the 2t, exactly the same. So I have to multiply by t here. Now, even though if you multiply by t, we still have t squared here, and there's a t, right? That's still not enough, because we still have t e to the 2t here. That is the same as that. So to make it linearly independent, we have to increase the power one more, so t squared. By that out, we have t cubed over t squared. Now when we look at this, e to the 2t and t e to the 2t, all are linearly independent now. All of that, these two, and these two, all of them are linearly independent, which is good. So if we have to guess, this is what our guess solution will be. Or that, of course. Right? But we're not going to guess, use the guessing method here. We're just still using variation parameters. Even though if we can guess, variation parameter still works. So y1 and y2 like that, and complementary solution c1 y1, c2 y2. So c1 e to the 2t plus c2 t e to the 2t. Right. The important things here, of course, y1 and y2. That's the first step. Second step, particular solution. We take the form of variation of parameter. Once again, this is equal to 1. So in this case, we have, of course, so for v1 and v2, where we have the system of equation. y1 v1 prime, y2 v2 prime equal to 0. y1 prime v1 prime, y2 prime v2 prime equal to the input function, which is going to be that. Yeah. So that's why I want the leading coefficient to be 1. In that case, that's just the input function. Will be a lot more convenient to do. Right. So system equation, Cramer's rule. So there will be a bunch of W's. The first one, y1, 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 y2, y1 prime, y2 prime. y1 e to the 2t, y2, that's not going to be simple. Derivative 2 e to the 2t. Derivative of this has to be a product rule. Derivative of the first and then plus the first with derivative of the second. Right. E to the 2t, t e to the 2t, 2e to 2t, e to the 2t, plus 2t, e to the 2t. Right. So multiply. We have e to the 2t times e to the 2t is e to the 4t. just add the exponent 2t plus 2t, that e to the 4t, and then plus e to the 2t times 2, so that plus 2 t e to the 2t, and then subtract the other direction. Sorry, e to the 2t times e to the 2t, he make it 4. And then subtract the other 2t, e to the 4t. Or conveniently, they cancel out. Besides, the Wronskian have to be linearly, the Wronskian cannot be equal to 0, otherwise they are linearly dependent and it's not going to work. We need linearly independent. Right, so that is W1. Replace that. Into y1, y1 prime, y2, y2 prime still there. Zero t plus 1 e to the 2t. Y2, what is y2? Oh, t e to 2t. And then y2 prime is going to be this. Well, cross multiply and subtract, so this will be negative t times t plus 1 e to 2t times e to 2t is e to the 4t. That is W1. W2. For W2, I will replace the last column into Y2, Y2 prime. Be equal to 0, t plus 1, e to the 2t. Right, y1, e to the 2t, 2 e to the 2t, 0, t plus 1, e to the 2t. Cross multiply and subtract, we just have t plus 1 e to the 4t, the other is 0. So the w's is not that complicated in this problem. Now once we have all the w's, Cramer's rule says the solution will be, this case solution for v1 prime is w1 over w. W1 is that over w. Well, that's convenient. Yeah. Even though I did say that. Sorry about. Okay, that's better. Even though I did say that, what happened? Yeah, look it off. Even though variation parameters we cannot guess, but still that's we can only do some certain kind of function. If we just throw any random function here, chances are that we cannot integrate. So the solution, of course, should be a little bit reasonable where we can actually integrate. If it's too complicated, then yeah, it's not practical. Because I can multiply this out. Now if that is the derivative, I can easily get back to the function by integrate that. So what do we have here? So that will be negative 1 over 3 t cubed minus 1 over 2 t squared. Power rule. Don't need a constant c. Right. So what happened if we have the constant c there? It doesn't matter though. We just ignore it. Yeah, I will show that. What happened if we have the constant c? Right, W2 over W So that's what we have t plus 1. Yeah, just t plus 1. So we get back to v2, just integrate t plus 1. So give us 1/2 t square plus t. Right. So we have v1 and v2. Now put back into the particular solution. v1 y1 plus v2 y2. v1 that y1 e to the 2t plus v2 y2. Right. Now, what we see here is the common factor of e to the 2t. I can factor them out. So be negative 1 over 3 t cubed minus 1 over 2 t squared. 1/2 t squared times t, so plus 1/2 t cubed plus t times t, t squared. Now, 1/2 minus 1/3. One half minus 1/3 should be 1/6, but I just want to do that. Yeah, so that's 1 over 6 t cubed, and 1 minus 1/2 for t squared, so that gives us 1/2 t squared. Now, of course, I will multiply this out. So that equal to 1 over 6 t cubed e to the 2t plus 1/2 t squared e to the 2t. Now, we guess the solution in this form, right? Something times t cubed e to the 2t and something times t squared e to the 2t. So we guess in this form, and that's exactly the form that we get. So that's nice. In variation parameters, in this case, we don't have to solve for the undetermined coefficient. When we solve for this, we get the exact solution. We don't have to worry about the coefficient. Right. Now, what happens if we have the c in this case? Now, instead, if we have, let's say, if we happen to have a constant here, and what happens if there's a constant here when we integrate? Well, when we multiply it out, now remember cy2 here, that actually is part of the complementary solution. So if there is any constant there, we contribute it to, it will contribute to the complementary solution. So if there's, even though if there's a constant, that part belongs to the complementary solution. So it doesn't matter, we still have this as the particular solution. Yeah, plus and this is still fine because that is a part of complementary solution. So that's why we don't need to write a constant there. Bottom line is, when we have these two, we can write the solution. This is the general solution. Y equal to complementary solution plus particular solution. C1, Y1, C2, Y2, plus that. Right. So, once again, this is not difficult, a bit tedious. The difficult part is sometimes that we have to bump into something very difficult to integrate. So even the problem, as I said, we have the wider range of function where we can put here, but we cannot just put any random function there because we still have to do the integral, and the problem has to be some certain type of function that we can integrate. If we cannot integrate, we just give the answer that has the integral in it. Yeah. So once again, get the complementary solution, which y1, y2, then we can put in the system equation. To solve for that system equation using Cramer's rule, once we have the solution, integrate, and then we can put it back into the particular solution. Right, let's look at one more example. Right, this is the example. Find a particular solution. In this case, we don't need to write the last step. We don't need to write the last step of this. We don't need to write the last step because we can get a particular solution. That would be very good already. Right, so still the same thing. First step, complementary solution. So homogeneous equation. Once again, I prefer to have the 1 as a leading coefficient. If it is not, divide by that. So we have 1 here. Because when that equal to 1, we're just going to put that here directly into that, or otherwise there will be a few more complicated things. Just try to get 1 there. So auxiliary equation r square plus 3r plus 2 equal to 0. Now, r square plus 3r plus 2 equal to 0 look like I can factor as r plus 1, r plus 2. Simple enough, right? Equal to 0. So I can have r1 equal to negative 1 and r2 equal to negative 2. With that, y1 equal to e to the negative 1t, y2 equal to e to the negative 2t, except that this time it is x. And of course, the complementary solution C1, Y1, C2, Y2, C1 e to the negative x, C2 e to negative 2x. Right. Most important here is we need Y1 and we need Y2. So that's the first part. Second part is particular solution. Right. Take a look at the input function, sine of e to the x. Definitely we cannot guess any solution in that form. Yeah, we cannot guess that. So in that case, y is the variation of parameter v1, y1 plus v2, y2. Now we write the system of equation. If I did not mention enough, try to write small because this problem usually are very long. Equal to, if the leading coefficient is 1, we're just going to put the input function. I am sensing some iteration by Parks here. Maybe we have to do it. Right. So system equation, Cramer's rule. So for the W, y1, y2, y1 prime, y2 prime. y1 e to negative x, y2 e to negative 2x. The derivative negative e to the negative x, negative 2 e to negative 2x. 2 by 2 determinant, easy, cross multiply and subtract. Alright, e to negative 2x times e to negative x is negative 2, e to the combine the power negative 1 plus negative 2 is negative 3. And then the other direction minus a negative, so that's a plus. It's a plus. E to negative x and negative 2x combine, negative 2 plus minus 1 is negative 3x. Right. Combine like terms, negative e to the negative 3x. That is the W. It's not that bad. W1. We'll put the last column. In place of y1, y1 prime. y2, y2 prime will stay the same. Right, 0 sine of e to the x, y2 e to negative 2x, y2 prime negative 2 e to negative 2x. Multiply that 0, and so we have e to negative 2x sine of, no, this is the other direction is negative. Right? Yeah. W2, replace the last column into y2 prime. Keep doing that. Yeah. Even with all the color code. Zero sine e to the x. Y1 e to negative x, negative e to negative x, that's y1 prime, 0 sine e to the x, determinant multiply that e to the negative x sine e to the x. Right, now find the v or v prime. Yeah, it might not be pretty here. v1 prime is w1 over w, w1 over w, w1 over w. Negative negative cancel out, e to negative 2x cancel with e to negative 3x. Anyway, just move, because the negative cancel out, e to negative 3x at the bottom, move to the top. What I do here, just cancel the negative sign, move the e to the negative 3x from the bottom to the top, turn to positive. Oh, it's not that bad. This is not integration by parts. So e to the x, when you combine this, 3x minus 2x, 3 minus 2 is 1, and then sine of e to the x. Alright, so that is v prime. Now to get back to v, we integrate. This is just substitution. It's not that bad. Let u be e to the x. Derivative of u is the same thing. Multiply the dx over and solve for dx. Yeah, you might do substitution differently, but this is how I do substitution. E to the x, actually this is going to be equal to u. Now, that's fine, just leave e to the x there. Sine e to the x here sine u. Dx is du over e to the x. Right? If substitution works perfectly, we should not have any more x, and we do not have any more x. integral of sine u is negative cosine u. Be negative cosine of e to the x. That is v1. Right. Now, v2. v2 prime is equal to w2 over w w2 over w w2 over w right, that's going to be negative. Once again, I move the e to the negative 3x from the bottom to the top, turn to positive. It's going to be integration by parts. That cancel out, and that gives us e to the 2x sine of e to the x. Right now we integrate to get back to v2. Integrate that. Right. Now, what I do is we still use the same substitution, so I'm not going to write that again. E to the 3x, e to the x here, that's still u, and the x is still du over e to the x. So we use the same substitution here. That gives us negative. Actually, just keep the negative inside, doesn't matter. E to the 2x over e to the x, what's that? E to the x from the bottom, move to the top. Right? Don't mind with the u and x. So it will be negative. E to 2x and e to negative x. Combine that give us e to the x. Right? 2 minus 1. 2 minus 1. It's just an x. And then sine u. I said, don't mind about e to the x, because e to the x, that is u. So we still have u. Everything in terms of u, which is good. Now, integration by parts. So what is integration by parts? Integration by parts is integral of u dv is uv minus integral of v du. The problem with that is we already have u in the problem. It will be confusing if we write u. If we're going to use u again. So instead of use that, I will write integration by parts. T ds is equal to u is v t s minus s dt. Yeah, that is integration by parts. Yeah. Of course, the variable here, we just switch conveniently. Later on, when we use a lot of integration by parts, you don't want to write t and or s either. But for now, it's going to be that. So with that, t, we're not going to fit the solution here, so I need to add a few more space here. T is going to be one of them, and then what is the other? So one of them is easy to integrate, one of them is easy to differentiate. So if I let t equal to negative u, dt is negative du. If I get s, if I let ds is sine of u du, then integrate, I'll get s integral of sine is negative cosine. So that's what we have. Substitute into out from integration by parts of that is equal to ts ts. So we have negative u times negative cosine of u minus integral of s, integral of s, which is negative cosine u, times dt, which is negative du. So this gives us u cosine of u minus, oh, that's cosine of u du. Run out of space, so regardless, it's good practice. Right, so we continue and we will have u is what? E to the x, but let's just integrate first. E cosine of u minus integral of cosine is sine. Now we'll rewrite this as, this is v2. U is e to the x cosine e to the x minus sine e to the x. So I have v1, v2, y1, y2. Put all of that together. Y1, v1, should be v1, y1. Same thing though, but right, v1 is that. That is v1. v1 times y1 e to negative x plus v2 which is this y2. Right, so yeah, v1, y1, v2, y2. Now multiply this out. We have negative cosine. Keep doing that. Cosine of e to the x. Let's write off that again. This is not very. Multiply this gives us negative e to the negative x cosine e to the x. Right? Now multiply this together. E to the x times e to negative 2x. Combine the powers. X minus 2x is negative x. Cosine of e to the x. And then multiply that to give us negative e to the negative 2x sine of e to the x. Well, let's cancel out. So the particular solution, negative e to the negative 2x sine of e to the x. Sorry, just as I want to end the video, I forgot that this is trivial. That should be a plus, and then indeed cancel out. Right, so that's what we have for the problem. Right, so it's not that bad in the variation of parameters. Get the y1, y2 first, and then write the variation parameters. Then the system equation. To solve the system equation, we use grammar rule. Solve for all the w's, and then the v's. The v1 prime, v2 prime, we have to integrate. Depends on the problem. It could be complicated, but not much in this problem. So in this section, we cover quite a different type of solution. We have the complex solution. We have repeated root, and now we have two distinct real roots and different type of input function. So since we cover enough example, I will end the video here. As always, thank you for watching, and see you in another video in differential equations.